Okay, so in this lecture, we're going to talk about op-amps. Op-amps stand for operational amplifiers, and they're a new type of circuit element that we haven't covered before and you may not be familiar with. Op-amps are really cool. They're actually kind of like magic. They allow us to do math with circuits. So we can add, we can subtract, we can multiply, we can divide. We'll also learn to integrate and differentiate, basically using op-amps. And allows us to do this math with voltages. So electric circuits are your components for everything from computers to calculators, and how they do math, how computers do math, is through a lot of this circuitry and oftentimes using op-amps to do that. So we'll learn how to design op-amps that allow us to do these math functions, adding, subtracting, multiplying, and dividing first. How they work is they actually act like dependent sources. I have not covered dependent sources in this course. Dependent sources are something, they're source, so they either provide current or voltage, but they can change their current or voltage output based on some other input. So they may have that V would equal 2 times Vx, so it would equal twice a voltage at some other point. Or V would equal 1/3 of I naught, it would equal 1/3 of a current somewhere from it, which can be really weird with units, but it can happen like that. They basically don't have a set voltage that says that V out is always going to be 5 or V out is always going to be 2. It's based on some other voltage or current somewhere. So they can change their output based on an input from it. What op-amps look like in real life is this kind of thing here. They kind of remind me of little Star Wars drones or those little robots. They have 8 legs. They kind of look like spiders. So I can see 4 legs on this side, but there are also another 4 on the back side there. Those 8 legs correspond to this pinout diagram here, based on whatever type of op-amp you have. We will be using an LM741 op-amp in this class, but you could always Google another type of op-amp because their pin configuration might be different. So you first identify this by starting at the head of the op-amp where there's a notch, kind of like the head of your spider here, so you know which way to number your pins correctly. So starting from the head, the left-hand side pin would be pin number 1. So this guy would actually be pin number 1, then going down to 3, 4, and up on the other side 5, 6, 7, 8, like we have drawn here. We really care mathematically only about 3 pins out of those 8, which is kind of funny. We care about in the LM741 diagram what is pin number 2. It is called the inverting input. Okay, the inverting input, we'll learn what that kind of does mathematically, but it's represented by this negative sign here. Okay, so again, that would be this pin right there. And we draw it then in a circuit diagram, our op-amp, since we only care about 3 pins, our inverting input, our non-inverting input, and our output. We tend to draw op-amps as triangles like this to represent those 3 pins that we really care about. We kind of ignore the other ones, mathematically at least. So where there's a negative sign, that's called the inverting input. Anything attached to that pin there will be attached to the inverting input. Anything attached to the one that has a positive sign is called our non-inverting input. I know that's kind of annoying. It's like unsweet tea. It's named by what it isn't. It doesn't invert a sign. And then we have our output is the point of the triangle. Okay. There are other pins that some of the time in advanced configurations you will use, like this offset null, or this one here to try to balance things. We're not going to do that in this class, but there are 2 other pins you do always have to use with op-amps, even though you don't see them in the circuit diagram that looks like a triangle for them. They are the V minus and the V plus. Do not confuse them with the inverting input and non-inverting input. This is not the inverting input. Since it has a V next to it, this is a negative voltage supply. The V positive is a positive voltage supply. Our op-amps, I said, can kind of be like magic and allow us to do math. Well, they don't do that magic without power. So just like you have to plug in your laptop for it to work, or a TV, or anything else electronic, Op amps do not do their magic of multiplying, adding, or subtracting or anything unless they have power supplied to them through a voltage supply. So we normally give it both a positive and a negative voltage. Most commonly, we use positive and negative 15 volts. Some of the time you will see this on your little triangle diagram for an op amp with an extra line vertically will go to the positive voltage supply, that's V plus, and another line going down, that's the V minus supply. Okay. Again, without giving it those voltage supplies, our op amps will not do what we think they do from it. So they do always have to have a voltage to power them. Okay, with our op amps, we have some rules for how they behave ideally. Again, nothing really behaves ideally fully in the real world, but these can be pretty nice assumptions to get a pretty close theoretical estimate for how they will work doing our math. Rule number 1 says no current at all can enter, and I'm going to add enter or leave. It really doesn't matter the direction of that current. The op amp at the inverting or non-inverting inputs. So remember, this is my inverting input, this is my non-inverting input. This means even if I have something like a resistor attached to these guys, any current through there has to be 0. Cannot have current go into those inputs or the other direction for them. The direction doesn't matter, it's just there can't be current directly attached to those inputs. Op amps allow us to do math, as we said, and one of the cool things about that math is they can get a voltage that can be amplified. So it means their V out, which is the point of that triangle, we call the voltage there, V out, could in theory be up to infinity. Now, in reality, they will never actually get a voltage up to infinity. That would be scary. But in reality, the voltage cannot exceed the voltage supplied in the power. So remember we said we had to have a power supply of V positive and V negative, which normally we're going to use positive and negative 15 volts. But if you had other voltage power supplies, you could use a different range. This means that really V out must be less than or equal to 15 volts and must be greater than or equal to negative 15 volts. In theory, it can be infinity, but in reality, it's limited by that power supply. Because we don't always write the power supply for an op amp when you're doing theoretical calculations, if you don't know what the power supply is, you can assume that V out can go up to infinity. Rule number 3, inverting and non-inverting inputs will be held to the same voltage if a feedback loop is present. And there should always be a feedback loop that goes from our output to our inverting input. So here's my output. I should go to my inverting input. Most of the time there's a resistor connecting between that, but there could be a capacitor, it could just be a wire, it could be a combination of resistors and capacitors, whatever from it. But this is called our feedback loop. Okay, it should always go from our output to our inverting input, not the non-inverting input. It's really comparing the output to your inputs and making sure that our output doesn't just keep on going up to infinity or something from it. If this is true, then any voltage you have at your inverting input, so again, let's say we have a resistor here. The voltage at this point, I'm going to call it VA, and the voltage at your non-inverting input, I'm going to call that VB, have to be equal to each other. So the inverting and non-inverting inputs will be held to the same voltage if you have that feedback loop. What that really means is that VA has to equal VB. Voltage right there has to equal the voltage right at our non-inverting input if there's a feedback loop present. And that's really helpful for helping us solve our op amp circuits. Rule number 4 is that infinite current can leave the op amp at the output. So although we said we can't have current at our inputs, our non-inverting or inverting inputs, our output here, I can have current here. And it can technically go up to infinity going through it. So stuff can come out or into here. The direction doesn't matter from it. Also note, when we're doing op amps, we can't do mesh analysis most of the time because we won't have closed loops. you have an op amp kind of in the middle, and you don't know what happens over that op amp necessarily. But we can do nodal analysis. I know this is kind of a bummer because most of you like mesh analysis, but mesh analysis doesn't work well with op amps, so we will have to do nodal analysis most of the time. Okay, let's look at an example of an op amp. So here's our op amp. Again, looks like a triangle. We have our non-inverting input here, we have our inverting input here, and we have our output right here. It's connected in a circuit with these resistors and a voltage source. I'm going to use my op amp rules to solve for this. So the first thing tells me that if I have a feedback loop, we said our voltage at our inputs had to be the same. So if I call this one VB, just because that's what I had it up there before, and this VA, the voltage right at this node and the voltage at this node, do I have a feedback loop? Yes, I have a path from my output, goes through RF, why it's called RF is it is my feedback resistor, to my inverting input. Since that's true, VA must equal VB if I can find that voltage. Well, do I know either of them here? In this case, yes, I do. VB, I've only gone through wire, is the same as VN, whatever this voltage source is. So both VB and VA will have to be equal to whatever that voltage source is VN. If VN's 5 volts, then that would equal 5. If it's not, it would equal something different from that. Okay, our other rule says no current goes into our inputs. So if I had current here, that would be 0, and any current directly into that input would also be 0 here. But I can have current other places. So let's label a current here, I1, and let's label a current here, I2. When it gets to this node, I1 can either go up, but we just said that current's 0, so it's really only going to go to the right. So I'm going to look at this node right here and write a nodal analysis equation for it. What currents are going into that node? Now it's I1, it's the only thing going in. What's leaving that node? Well, I have I equals 0 because I can't have any current go actually into, in this case, my inverting input of my op amp. So 0 plus, also what's leaving this node is this I2. Those are the only possible branches out. So I1 basically has to equal I2. Now I need to write those based on nodal analysis as a change in voltage over resistance. So how do I write I1? I1 starts down here and goes to up here. Voltage down here is ground. It's like 0 volts. So it goes from 0 to what's my voltage here? Well, this was all just wire. That voltage was VA. So 0 to VA. VA, we said, was equal to VB, which is equal to my voltage input. So I'm going to write it instead of as VA or as VB, I'm going to write it as VN. Again, that came from down here. Over what resistance? That resistor is called RN here. That's just how I write I1. So equation has to equal I2. I2, based on its arrow, starts at VA, which VA again is equal to VB, which is equal to VN. So it starts at VN, and it goes to some voltage over here, which I'm going to call V out, the voltage at the output of my op amp, which is normally what I'm always trying to solve for, over RF. That was my feedback resistor here. Okay, now I normally want to write this equation as V out in terms of everything else, so solving for V out. So to do that, I'm going to multiply RF by this side of the equation. So I'm going to have, and I really had 0 here, so I have negative RF times VN over RN now. And I don't have that equal to yet. What does that equal? That now equals, when I move RF to the other side, VN minus V out. Okay, I'm going to move VN to the other side, and I'm going to say negative VN minus RF VN or RN equals negative V out. Okay, I have a whole bunch of negatives, so I'm going to just divide by all my negatives, and I have Vn in both of these terms. So I'm going to pull out my Vn, and then what do I have multiplied it by to equal V out, positive V out? Well, I got rid of my negative sign. This Vn was just multiplied by 1 times Vn. This term is now multiplied by plus Rf over Rn Vn. This is my equation for how Vout relates to a voltage input that I had from my voltage source over here and the resistors in this circuit. Mathematically, what does this mean? This means I take a voltage input, again, maybe it was 5 volts, and I multiply it by 1 plus my ratio of resistors. So this is a way to multiply. I have this set of circuits. I can multiply with my op amps from it. Okay, what do I multiply my voltage input by? Well, it's multiplied by this whole term here. Let me use a new color. Let me use green. This term here is called the gain, which equals really the ratio of Vout over Vn. Or another way to think about it is, what did you multiply Vn by to get Vout? Right? In my case, if I move Vn to the other side to get Vout over Vn, I'd be left with this term. So if Rf is equal to 5 kiloohms and Rn is equal to 1 kiloohm, then what does this circuit multiply a voltage input by, no matter what that input is? Well, it would multiply by 1 plus 5 kiloohms over 1 kiloohm, which 1 plus 5 over 1 plus 5, 6. So if Vn was 5, it would multiply 5 times 6, and Vout would be 30. If Vn was 2 volts, it would multiply 2 by 6, and Vout would be 12 volts. That's how I work through my op amps. Let's do another example. Okay, I now have an op amp circuit that looks like this. Okay, using again our op amp rules, let's look at what happens here. So let's label some currents. I'm gonna label a current here. I'm gonna call that I1. I'm gonna label a current here, I2. And if you don't think about the little wire right there could be a little current there, but it's going directly into my input of my op amp, my inverting input. So that has to be 0. Let's label this guy and call it I4. Now, I4, does it have any choice but to go into an input of my op amp? No. So I4 is also 0. Okay. So if I4 is 0, what's the voltage? I'm going to call this voltage up here VA, and I'm going to call the voltage right here VB. What is VB? Well, I4 really goes from ground down here, 0 volts, to voltage, whatever VB is, over my resistance right now that's just called R. But I4 is equal to 0. Okay, so if R is not a 0 value, or infinity from it, which resistor can't be infinity, then VB must be equal to 0. So my voltage at VB is 0. By my rules of op amps, if I have a feedback loop, do I have a feedback loop? Yes, I do. My output to my inverting input. Then this VB also has to equal what VA is, right at my inverting input. So VA is also equal to 0. So now let's look at node VA. Write a nodal analysis equation for it. So current I1 is going into that node. I2 is leaving that node. Again, you could also write plus I3, but we've already established I3 is 0 because no current can go into my op amps. So how do I write I1 as a change in voltage over resistance? I1 starts over here. My voltage would be Vn, and it goes to VA. Now, VA, we just said, was equal to 0. So Vn to 0 over Rn. How do I write I2? I2 starts up here at this node. That was VA. VA again is equal to 0 because VB is equal to 0. And it goes to what voltage? It goes to the voltage at the output of my op amp, which I'm calling Vout over Rf. Let's solve this equation for Vout. So to do that, I need to multiply Rf by this other side, so I end up with Rf over Rn times Vn, so it's Vn minus 0. And I still got to get rid of my pesky minus sign, so it's really minus this whole term. What did this op amp do? Well, it still takes a voltage in, and it multiplies by a ratio of RF over RN. I didn't have that pesky 1 plus RF over RN that I had in the previous circuit, but it also multiplies by a negative sign. Because of that, it is called an inverting op-amp. Our previous setup of an op-amp, the slide we just did before, oops, that's the plus. Erase that part. That was the minus. This was our previous op-amp. Going to ground here. RF, RN. Yeah. Here we had a voltage in connected to our non-inverting input, and we got that Vout was equal to 1 plus RF over RN times Vn. We said it could multiply, and what it multiplies by is a gain called 1 plus RF over RN. Here, my gain is negative RF over RN. And because that's a negative sign, it inverted my sign from my voltage in. So if Vn is positive 5 volts, then Vout has to be a negative sign. If RF, let's make it 2 kiloohms, and let's make this one 1 kiloohm, RN 1 kiloohm, then it would multiply by 2k over 1k, or 2. So it would be negative 2 times 5, and I would get negative 10 volts. Okay, this is called an inverting op-amp. Our first circuit, this guy, inverting op-amp. I can't write well with this pen now. Amp. Our first circuit we just had on the previous slide is called a non-inverting op-amp. Why is it non-inverting? Well, because I don't flip the sign here. It stays the same sign. If Vn was positive, then Vout's also positive. Vn's negative, Vout's also negative. Here, I do flip the sign because of that. So those are my differences with it. Okay, let's do another one. I have this setup. I'm already going to tell you what it is called in our op-amp world. It is called an inverting summer. And it has several different voltages. I've labeled them V1, V2, V3. It helps you to think about it. It could be attached to a voltage source here. It's called V1, and this one's attached to V2, and this one's attached to V3. I'm just labeling the voltage at that point and calling it V1, V2, V3. Okay, and this is our voltage at our output for our op-amp, that little point of the triangle. And I want to see what happens here. Well, no current goes into my op-amp. So if this current is 0 and I have no resistance, this is also 0 volts. And this is 0 volts because I have a feedback loop. It means my inverting input will be held to my non-inverting input. Now let's write some equations for current. I'm going to call that I1 through resistor 1, I2 through resistor 2, I3 through resistor 3, and we'll call it I4 through RF. Looking at this node here, this really whole thing is a single node, right? What currents are going into that node? I have I1 plus I2 plus I3. What's leaving it is I4, that current through that feedback resistor. Okay, so how do I write I1? I1 goes from V1, or if you want to think about it as our voltage source, to the voltage at that node, which we've already said is 0 volts. It has to be the same as my non-inverting input. My non-inverting input is connected to ground. No current can go through. So it goes from V1 to ground, or 0 volts, over R1. I2 goes from V2 ground over R2. I3 goes from V3 to ground over R3. And I4 is the special one. It goes through our feedback loop. It starts at 0 volts and goes to Vout. So 0 minus Vout over RF. Solve this whole equation for Vout. So we calculate what Vout is based on our inputs. In this case, I have multiple inputs, V1, V2, and V3 from it. I need to multiply by RF and multiply by a negative. So I end up with big fat negative. Each term gets multiplied by RF here. Move it to the other side. So I get RF over R1 onto V1 plus RF over R2 onto V2 plus RF over R3 onto V3. And this could actually continue if you had a zillion resistors with their individual voltage sources connected to that inverting input. What did this guy do? Well, he took several different voltages, V1, V2, V3, he multiplies by a factor and inverts by the sign from it. So it's called an inverting summer. Inverting because my sign flips from my voltages and my inputs, V1, V2, and V3. I have multiple inputs here. And it sums V1 plus V2 plus V3. If all I wanted to do is really do math said V1 plus V2 plus V3, then all I have to do is make my ratio of resistors equal 1. So RF over R1 would just need to equal 1. It would have a big negative though. It would still flip my sign of that sum. And RF over R2 would equal 1, and RF over R3 would equal 1. If I didn't want to multiply by anything, but really multiply by 1. So that's my inverting summer. It allows me to add now voltages together and multiply if I want, but it does flip the sign. We now get to our most complicated op-amp circuit. This is called a difference amplifier. Now your book does go through a proof of how it gets to this scary equation. I'm not going to go through it here because I never require you to go through the proofs for these, but if you look it up, V out here, so the voltage at my output will end up equal to R1 onto 1 plus R2. That's a 2. Make sure we can read that as 2. Over R1. That whole thing over R2 onto 1 plus R3 over R4. That whole term gets multiplied by V2, and then minus R2 over R1 V1. It is a whole big, oops, nope, that is supposed to be, I put my which resistors which in this diagram compared to your book. As R1 over R2 times V1. That looks like a big scary mess of equations, and I can't really easily see what it's doing to my voltages. It multiplies by something, but it's kind of weird. However, this equation can become not so scary if you have a special case for your resistors. So if and only if R1 over R2 equals R4 over R3, then my equation simplifies a lot. V out just equals R1 over R2, with the same ratio as R4 over R3 in this case, times VA minus VB. Again, VA is a voltage over here. It could have been a voltage source you're attached to, and VB right here. But what this does is takes a voltage VA and it subtracts another voltage source that you have VB and multiplies by a factor. Because it subtracts, this is a difference amplifier. Okay? It is very useful, particularly with biomedical measurements, to measure a difference of voltage in 2 points. You would tend to use this with something like an EKG, so you can measure the voltage difference between different sides of the body from it. That I can subtract the voltage at one point to another and multiply by something to make it larger. So let's say, in our special case, if R1 over R2 is equal to 10, then that's R4 over R3 as well. So you could add R1 was 10 kiloohms, R2 was 1 kiloohms, and R4 could have been 20 kiloohms, R3 being 2 kiloohms. They still have a ratio of 10 to both of them. Then what this would do, it was take my voltage at one point, what was connected, I wrote these the wrong way. This should be, sorry, VB minus VA. And so V2 here is actually VB, and this is VA. I didn't write it based on what this diagram is here. VA is what's connected on the other side of your resistor to your inverting input. VB is to your non-inverting input. Takes VB, it does not invert the sign for it, so VB is positive, and it subtracts VA, multiplies by something. That's our difference amplifier. Okay, this may seem a little confusing right now. We'll do some more op-amp examples in class on Monday. Good luck, guys.